We are now starting a series of chapters that are for circuits. That means it's going to include capacitors, resistors, and power supplies. Chapter 5 starts off with capacitors. Chapter 6 starts off with resistive elements and power supplies. And then Chapter 7 starts looking at techniques of solving resistive circuits. So Chapter 5 is on capacitors. But in this lecture, we're going to focus on just capacitor fundamentals. So the first question is, what is a capacitor? And one of the ways that we can answer this question is by using an analogy. When a spring mousetrap is set, the work done to set it up is stored as stored work, but we call it spring potential energy. In a similar manner, the work done by a battery is stored as electrical potential energy inside a capacitor. We say that it's in the field. So a capacitor, and sometimes you'll hear me say the word cap, is any two conducting, or just two conductors, but the most important one is parallel plates. So we have two conducting plates separated by a dielectric. So to store this electrical potential energy in this device, one transfers charges onto the plates, where we have an upper plate where the upper plate is positive and lower is negative. The energy is stored in the field. Now you could say the electric field. I prefer the potential field, but picture-wise, I imagine something like this here. So I have a plate. That's my upper plate, and I have a lower plate. And let's color code them. So let's say that I'm going to color code that yellow, and this one will be gray. And now I have a wire. So it's the wire that I need here to transfer charge. So on the upper plate, we're going to get a positive charge that's distributed. And on the lower plate, we're going to get a negative charge. So these two guys are the conducting plates. Now, right now, the way I've drawn it here is that I have air as a dielectric, which is fine here, but when you purchase a capacitor, it's not air. They typically sandwich a dielectric. So in here, there's a dielectric insert. So capacitors have a tremendous number of applications. It's vast. So I'll just give you sort of like a category of things. So the first one, we'll talk about what is called a quick recovery of energy. In the old days, they had an array of capacitors that would, do camera flashes. Now they do it differently, but we could say that a quick recovery of energy would be a camera flash. The other thing that it could be a keyboard. It could be a touch screen. It could be just a number of things here. And what you're going to find here is that a lot of times, because we want quick recovery, these guys have smaller capacitors. Then we have other uses for capacitors. And we could say that this is a slow recovery of energy. You know what? I shouldn't say recovery. I should say release. That's a better word than recovery. So I'm going to say a quick release. So here it's a slow release. And again, the applications are just phenomenal in what we can do. But one of the ones that I'm sure you have in your house is a surge protector. From sudden electrical impulses, maybe jolts of power. In this situation, these are typically larger capacitors. And, just one more, but again, there's numerous ones, is the other one that's really common here is that we can set up what is called a resonant circuit. And here you have to ask your question, how can a radio pick out one slash single station when there's numerous ones. It turns out that, if you talk about, in older situations, they had a variable capacitor. And because they have a variable capacitor, you can do that. So again, the list goes on, but I'm not going to look any more than that. So the first thing we have to do is that we have to define current. We have to first define electric current. In circuits. And the reason why we have to do that is because we've been talking about that the motion of charges occurs with negative charges. Unfortunately, that's not the way circuits operate. So there's two conventions. The first one here is what is called the conventional current. So the conventional current is the movement of positive charge. Well, this could be problematic because when we talked about in the previous 4 chapters, positive charges don't move because those are the protons. But that's not the way current is defined. This is the standard choice. So it's going to take a little bit of adjustment. The other one, the one that we've been talking about so far, is called the electronic current, is the movement of negative charge. That's not the standard choice. So just to say a few words before moving on here, the assignment of negative and positive to charges is arbitrary. And it could have been the other way. Now, the story is complicated, and the reason why it's complicated because you have to go back and look at the work done by Galvan, which effectively started the first battery, but most of the blame falls on Benjamin Franklin for this reason. Again, the story is complicated. History is never that simple. But because it's arbitrary, because it is arbitrary, either choice presents no problem whatsoever. That being said, For students learning this, for the first time, it is initially problematic. It's just an adjustment period. We'll go more into this in chapter 6 and 7. So now we want to look at these fundamentals, okay? We want to look at the fundamentals. And what I'm going to say, and I'm going to do this over some chapters here, is that, so when I say the word capacitor, fundamentals, I really mean that it means several things that we have to tackle. The first one is that we have to look at what's called the capacitor equation. And the capacitor equation essentially talks about the proportionality between charge and voltage. And then once we have that, we then want to apply this to the parallel plate capacitor. The most important one of all of the capacitors. Why? Because it's the easiest to do this. And then we want to come in and we want to start looking at what we mean by capacitance. And you're going to see that capacitance is really what describes the characteristics of a capacitor. And then finally, we're going to ask, how does a capacitor get charged? And what's really important in this situation is that we have to start looking at the current in the circuit, which is important. So the first thing I'm going to start off with is that I need to get to the capacitor equation. And so the way I'm going to deal with this is that I'm going to deal with what's a parallel plate capacitor. So the first thing that we're going to look at is we're going to look at a capacitor equation. And you're going to see that this capacitor equation is the main equation for capacitors. So capacitors come in many flavors. And what you're going to see here is that the common ones is what is called a parallel plate. So we drew a parallel plate already. So if I just come up here, and if I grab this guy, this right here is a parallel plate capacitor. So I have a parallel plate capacitor right here. Now, I'm not going to worry about charge right now. I'm just saying this is the shape right here. So this is the most important one. And this is where I was saying that this guy right here is the parallel plate capacitor. Now, there's a conceptual capacitor. So this is known really only in concept. So this is a conceptual spherical capacitor. And so if you were to look at that, it looks exactly the same thing. We need two different plates, but in this situation, we have a sphere, and then the yellow turns out that that's going to be the high potential. Let me move this guy down. And then I'm going to have a shell, a conducting shell on the outside. And you'll see here that I'm trying to color code these so that they're exactly the same. So the shell here is in gray and it operates as the lower plate. And so inside of here is the dielectric. But this is really in concept that we want to look at a spherical capacitor. Now, the other one, which is very popular in circuits, is a cylindrical capacitor. So if I think about a cylindrical capacitor, I'm seeing that I have a cylinder. In this case, it's a very squatty cylinder. And what you're seeing here is that there's the yellow portion, and then the outside is the gray. So again, this guy tells me about the upper plate. This guy tells me about the lower plate. In a very similar way here, this acts as the lower plate, just like this right here acts as the lower plate. And then right here, you're seeing that this guy's acting like the upper plate. Very analogous. So then inside of here is our dielectric. And so typically when we talk about a dielectric, we use the symbol or the permittivity constant, which we'll talk about more later. So this guy here is a cylindrical capacitor. So now we want to focus on the details of the parallel plate capacitor. So a parallel plate has the following details. So when I look at the upper plate, what I'm seeing here is that I'm seeing that I have a plate. So when I'm looking at my plate, I'm looking at this guy here. So if I draw the same thing here down below, I'm now seeing two plates. There's my upper plate right up here. Then there's my lower plate right in here. Now, I'm not putting in a dielectric right now because I want to look at the geometry of the plate. And what you're seeing right here is that on this plate, we have an area A. And another thing that's important about this capacitor here is that there's a plate separation which is typically symbolized with the lowercase d, and then we have a wire. So this guy right here is the wire. So when we connect this to a power supply, what do we have? So when connected to a battery, and typically these are known as power supplies. So when it's connected to a power supply, positive charge transfers to the upper plate and simultaneously positive charge leaves the bottom plate. And when it does this, you're going to find that this results in a negative charge for the bottom. So if I was to draw a picture of this, I would then say something like this. So let's draw this circuit here. I have my power supply. And this power supply has a positive and a negative. And we say here is that this is the voltage of the battery. I typically don't write it this way. I typically just write it that this is the source of energy in the circuit. So now what happens here is that I have parallel plates. So what this tells me here is that I have a parallel plate all the way across here. And then I have my wires that are then going to connect to this circuit here. Now, if I set this up, this is my upper plate right here. Here's my lower plate. There is a gap in the circuit. Capacitors are these strange things that there's a hole in the circuit, and yet it has all of these properties. But here we'll say that there's a dielectric, but that still presents a hole. Now, what you're going to find here is that when I look at the circuit, what you're actually seeing here is that there are already charges everywhere in the circuit. So as soon as I turn on the battery, these guys start to move, but they move everywhere, just absolutely everywhere. And so what happens here? What happens is that I build positive charge on the upper plate, and that's because I have incoming positive charges, and on the other hand, I build negative charge down here at the bottom because on this plate here, I find that I have outgoing positive charges. And the reason, what's strange about this is that the goal of the dielectric, The goal of the dielectric is that no charges passes through a dielectric. So it is literally a hole in the circuit. So now what I want to do is that I want to look at this guy a little bit more carefully. So I'm going to copy this and then I'm going to adjust this thing. Because this can be a tricky situation that we're going to be talking about. So here we go. So now let's clean this up a little bit. And what am I actually seeing? Well, I have a wire. And so what happens here? I have positive charges that are coming in. And I have positive charges that are going out. So I'm seeing these guys coming in and these guys going out. So if I look at this, we can see here is that this is incoming and this guy is outgoing. And the fact that we develop positive and negative charges, we can treat these as infinite planes if we're looking right at the middle. So then this has a net positive charge. This has a net negative charge. And as a consequence, between these 2 points here, we get the voltage of a capacitor. And I typically don't write the capacitor word, I just write C. So once again, why do we have a positive charge? Because we have more positive charges on the top plate. And on the bottom plate, we have less positive charges, which then gives you a net negative charge. So there are 2 details that we should think about. That I did not mention. The first detail I would say is that the amount of charge on each plate is exactly the same. So when I look at this thing, what this tells me here is that if I look at the total charge of the capacitor, it's equal to the charge of the upper plate plus the charge of the lower plate. And what you're going to find here is, but they're equal and opposite. So then this becomes what? This becomes a positive of the upper. And then this guy is the negative of the lower. And these guys are exactly 0. So a capacitor has a total charge of 0. So in other words, the total charge of a capacitor is 0. So once again, when I look at my plates, let's see if I still have that image. I do, so let's clean this up a little bit. So once I clean up this image here, we're seeing here that this guy acquires a positive Q. This one acquires a negative Q. And so when I look at the absolute values of these guys, I get that this charge and this charge are exactly the same. So the second thing here is that current will not go through the dielectric. As long as the voltage that is the voltage of the capacitor does not reach the dielectric breakdown value. Now, if you look at parallel plate capacitors, they typically have ranges for dielectric. They'll say that the maximum voltage is somewhere under 100 volts. So, for example, assume the breakdown voltage is, let's say, 50 volts. Then this is what it means. Then, if I have a capacitor where the voltage of the capacitor is less than 50 volts, then that means that there's no dielectric breakdown. And no current passes through the dielectric. So in this case, we then have this type of scenario here. So let me copy this guy here. And then we'll just put this guy right in here. And we'll just sort of like modify this just a tiny bit. And so in this scenario here, if I'm looking at this guy, and if I look at the polarity of this capacitor, so if the voltage of the capacitor is less than 50 volts, then no current passes through the dielectric. And so then that just means that the picture that we talked about up here is what's happening. Charge comes in, charge goes out of the lower plate, creating that difference here. On the other hand, if the voltage of the cap reaches 50 volts, then that means dielectric breakdown has occurred and current passes through the dielectric. So again, using this guy right here, we then have a circuit like this. And in this situation, we now say that it's equal. So when it's equal, then what you're going to find here is that there is current that's moving from the upper to the lower. So I'm going to say that this guy right here, this is current passing through dielectric. At this point, the capacitor is no good. The capacitor is no good and should be disposed. Of course, you dispose of it properly. So now we're on the final piece of this lecture here. We now want to talk about the capacitor equation, and that was the goal of this chapter. So now we're going to talk about the capacitor equation. And you'll see here is that the capacitor equation has two pieces to that. So the capacitor equation is the fundamental framework that all capacitors follow. There is a characteristic equation that describes all the details of a capacitor. This is called its capacitance. But it follows a different equation, and we'll talk about that in the next lecture. But for right now, I only want to look at the capacitor equation and sort of talk about the proportionality constant. And so in this thing here, we are going to have to define this capacitance, but it doesn't have all the details. So now let's review something we already know about the connection between charge Q and voltage delta V. So let's look at this. So you could imagine that I have two spheres. Okay. So I'm going to imagine that I have two spheres. So let's say I have a sphere here. And I have another sphere right here. And so what I imagine is that I put charges on these spheres. So in this case, let's say that I have this amount of charge. In this case, I have more charge. So when I'm looking at this charge, I'm seeing that this charge is little, but over here, I have more charge. So what does this really tell me here? So if I have a small charge versus a large charge, what does this tells us here? Well, the first thing that it tells us here is that if I now look at these charges, right? So if I come in here and I copy these charges, and let's say that I paste them right here, what do I expect to actually see here? Well, what I expect to see is that if I look at the E field of this one here, when I look at the field lines, there's not as many. These guys, because I have more charges, I'm going to have more field lines. So in other words, this tells me that in this case, I'm going to have a weak E field. Over here, I'm going to have a strong E field. Not a surprise. But now, what does this tell us about the potential? So if I look at the potential of this, and I start using an incline for a constant E field, then what I'm going to see here is that I'm going to have an incline. In this case, because I have a small field, my incline here should be very shallow. In other words, if I come in here and I look at my incline, the height of this guy should be very small. That is going to give me a small potential. And the reason why is that there's just not very much charge at all. So we say that because of this reason, this gives us a shallow potential incline. On the other hand, if I have a lot of charge, then these guys have to be separated quite a bit, right? So if I take this charge here, let me see if I can do this, that height has to be higher, right? It has to be higher. And because it's higher, if I compare this to the ground here, we're going to say that this height right here must be higher to account for the more charge. So what do we say this is? This should have a steep potential incline. So in other words, we are seeing that there's a connection between charge and the potential incline, or the height of the incline. So again, I expect you to already know this, but we're just reviewing briefly. This should not be a surprise, since more charge leads to a larger voltage. A higher height to the incline. What's unique with capacitors is the charge to voltage ratio is always a constant. And in this case, this is a constant of proportionality. In other words, if I look at this ratio here, that is the charge to voltage, this is a constant. And all this is saying here is that if I have a little bit of charge, I'm only going to get a little bit of voltage. But what's amazing is that even though these guys are proportional to each other, they equal the same constant for the same capacitor. So what I'm saying here is that this constant is the same for the same capacitor. That ratio does not change. Now remember, it doesn't have to be this way, but nature dictates this for capacitors. So because of this uniqueness, this new proportionality constant is defined as the capacitance. So then, by definition, we can then say that the charge to voltage ratio, this happens to a lot with capacitors, and so then this term capacitance is defined with this symbol C, which really just tells us here is that we have a new constant, the capacitance, which is equal to Q delta V. And I typically don't remember it this way. I typically rewrite this as the charge is equal to the capacitance times the voltage. This is called the capacitor equation. Okay, so this is the capacitor equation. I mentioned this just a little bit earlier. This is only half the story. Okay, I'm going to say that this here is only half the story. In the next lecture, we'll get to the second half of this thing. So now let's just interpret this thing. So what does this thing start to mean here? So I want to do an interpretation of the capacitor equation. Well, I would say, one, I would say that the capacitance is a measure of a capacitor to store a variety of things. One, people say it stores charge. Two, it stores electrical potential energy. And three, some people say that that it actually sets up a potential field, right? That it stores voltage. So I would say that this is probably the most commonly stated, but I prefer to talk about energy. So I say it's not about storing the charge. It's the energy is not in the charge. The energy is in the configuration of the charge. But I would say that this here is the actual stored work. And that's what we say. So that work could be stored in the electric field, or it could be stored in the potential field. And so if I start to look at this thing, then we say this here. So if we have a small capacitance, then we have all of these sequences that start to happen. That means here I have less charge on the plates, or I could say that there's less electrical potential energy stored in the field. Again, that is my preferred way of looking at this. So now, if I have a large capacitance, then the big difference here is that I have more charge on the plates, and therefore more electrical potential energy stored in the field. So all this is true. You'll see that the details of the work of the field of a capacitor is somewhat subtle. And when we go to look at that, we'll address it in the next lecture, but it's subtle how we actually look at that. Now, I want to leave you with a conceptual analogy. Okay, so this is a conceptual analogy between buckets of water versus charge on capacitors. So there's what to sort of like ease this, we can actually take somewhat of electronics and plumbing and make a good analogy about this. So I would say that a capacitor can be like a bucket of water. You can fill it from the top and drain it from the bottom. And so this is kind of what I'm thinking about here. So if I look at a picture, we could imagine that we have a bucket. So let's say this is our bucket right here. And so as I'm looking at my bucket, I have a drain right here, which we will just do this here. Now, if I pour in water into this thing, what do I see here? Well, what I see here is that water comes in from the top. And then with the drain, water comes in the top. And then here it leaves the, I don't know, what do you call it? The drain. right? It leaves the drain here. Now you got to be careful with analogies. Analogies can be slippery. So now let's compare this to the capacitor. So if I have a capacitor, I can say similar things here. So you could see here, this is the top of the capacitor. And then here's my wire. And then this is my lower plate. And then here's my wire. So what do I have? I have incoming charge. And I have outgoing charge. So they're similar in a lot of ways. So if I look at the size of a capacitor here, excuse me, the size of the bucket, we then say that the size of the bucket is rated in gallons. I could then say that the size of the capacitor is rated in farads. Okay, so again, we're really comparing these two guys. So here we go. So when I think of a bucket, I'm going to be comparing these two right here. So let's talk about the first thing. Let's talk about the capacity to hold water. So if I hold water, then we talk about the volume of the bucket. And so what I could imagine that if I'm doing this, so let's look at this analogy first here. So what I have to do here is that I have to compare a smaller versus a larger bucket. So here we go. Let's say that I have this bucket right here. And you can clearly see that this guy is fairly small. So this is only going to hold a little bit of water. On the other hand, what if I have a bucket that looks like this? Well, that's a much larger bucket. And so when we think about buckets here, here's what we're seeing here. We talk about the volume of a bucket, and we know that the volume has to be area times the height of the bucket. So if I have a smaller bucket, we then say that it holds, so it holds less gallons. So therefore, it has a smaller capacity to hold water. On the other hand, the larger bucket, well, it holds more gallons, and as a consequence, it has a larger capacity. We could say the same thing about capacitors. And we could say here's the capacity to store charge. This is defined as the capacitance C of a capacitor. So then picture-wise, I'm just going to look at something like this here, where I'm going to say, I have a capacitor that looks like this. So when I look at it, that means this guy has the ability to store a certain amount of charge. That's small. But what if I had one that was much larger? So if I'm looking at this guy, I'm seeing here that I have larger plates. And because I have larger plates, I can put more charge in there. Right? So in this case, what we're going to see here is that this guy can place only that amount of charge. This guy, I can place a lot more charge onto this, so it has a bigger capacity to store charge. So then we say that if we have a smaller capacitor, then that tells us is that it holds less charge. And if it holds less charge, it then has to have a smaller capacitance. However, if it's a larger capacitor, it holds more charge, and therefore it has a larger capacitance. Okay, the last thing I want to talk about is that I want to talk the ability about applying pressure. So what we want to look at here is the ability to apply pressure on the outlet pipe. Now, what we're really comparing here is less versus more water, but we're really talking about the depth of the water. So let's look at this guy. So let's say that I have this little guy right here. I have a little bucket right here. So now what I'm going to do is that I'm going to keep the same area, but now I'm going to make it taller. So now if I fill this up, here's what I'm going to see here. The smaller one, this clearly has less water depth. And by the way, I wanted to make this larger, so let's do that. Less water depth. In other words, in this case, it has less water. And then what happens? If I have a less water depth, then I'm going to have less pressure exerted on outlet pipe. On the other hand, this has more water depth. In other words, it has more water. So then this has more pressure at the bottom. And so as a consequence, it's going to have a larger pressure. So now if I do the exact same thing here, I'm going to talk about the ability to apply voltage to, or let's say not voltage on charges. So in this situation, we're talking about charge that either has a lot of charge or it has less charge. So let me grab this image here and let's bring this down here. And so what I want to do here is that, let's say I put this down here at the bottom, and then I want to paste this guy up here, but now I'm going to take charges off. So I could imagine that I have less charge. And then this guy has more charge. So in this case, I'm going to have something like this. If I have less charges on plates, then that's going to tell me that there's less electrical pressure. And this less electrical pressure is what we call voltage. So in other words, the voltage on these guys is going to be small. But if I have more charges on the plates, then I'm going to have more electrical pressure or voltage, and I'm going to have a higher voltage.